And, so even if many of you don't really have much exposure to deep learning, my hope is still to convince you that there's a lot of interesting mathematical problems to study in the field, and that your expertise in random matrix theory or high dimensional statistics might be really valuable in addressing some of the open questions. So that's sort of the motivation. The plan is to begin with just a very probably too high level introduction to motivate studying backgrounds. And I'd like to just ask the question whether a couple of the mysteries that have dominated parts of the literature in deep learning over the last few years are interesting signals, or whether maybe they really should be thought of as backgrounds. And to do this, I'm going to introduce some very simple models. You don't really need any prior exposure to deep learning to understand what I'm going to be talking about, because it's basically just linear regression. But I'd like to set the foundation and give you some background so that we're on the same page. And so to begin, please indulge me with this short exercise. So suppose you ran a set of expensive experiments and you acquired some data that looked like this. Have you made a groundbreaking observation? Clearly the answer to that is going to depend on your prior expectations. If you expected some kind of upward trend, the data surely would be quite surprising. But what if you expected a downward trend here? Then really it's going to depend on what your understanding was of the background. That is to say, what you expected to see if nothing interesting were happening. And a thorough understanding of the background can filter out really boring results. And actually, if you make precise enough measurements and have precise enough background predictions, you can make important discoveries. So actually, this is data from the LHC at CERN in its search for the Higgs boson. And this little blip, in fact, is a 5 sigma discovery of a new particle. So a precise understanding of the background is really important for advancing science. And I'd argue that in a quickly evolving field like deep learning, we need to devote more effort to understanding the backgrounds before we can really be doing any kind of legitimate science. So with that, I'd like to just give you a background on some of the discussions that have been going on in deep learning, and paint a picture that I hope to shed some light on through techniques that I think everybody here should be familiar with, and hopefully give you some perspectives on how such tools can actually help advance this field. So, excuse me. Yeah, so when I talk about deep learning, I'm referring to basically deep neural networks, or even not so deep neural networks, basically just neural networks generally speaking. And in practice, the models that people use are big. People think of them as defining a very flexible class of functions. And of course, it's hard to put a quantitative metric on what that means, but a very crude way of doing that is by counting the number of parameters that define the model. So in this, by now, 5 or more year outdated figure, you can see the parameter count of a number of image classification models that at the time were state of the art. And you can see they're leveraging hundreds of millions of parameters. Nowadays, state-of-the-art models that are used to generate natural language actually can be using upwards of 1 trillion parameters. So, I think there's no arguing, at least by some kind of common sense intuition, that the number of parameters in these things is large. But of course, large compared to what? And I think a natural answer to that question is compared to the number of parameters you would need for the problem at hand. And so an interesting set of experiments looking into that particular question was performed by Zhang et al. In 2017. And what they did is the following. They took a basically simple off-the-shelf convolutional neural network, one that is designed and typically does perform well at certain image classification tasks. But instead of training that model on an image classification task, they followed the same and standard training protocols, SGD, et cetera, and just trained the model on input-output noise patterns. Same amount of data, same dimensionality, et cetera, but instead of coming from natural image distribution, it was just kind of random Gaussian noise. And they found that those same models trained with the same training protocol were easily able to memorize the noise patterns. So what this said was that, within the same family of functions that these neural network architectures trained with SGD can realize, exist models that generalize well. They make good predictions on image classification beyond the training data set. And it also contains functions that are kind of crazy, just memorizing any input-output patterns and don't really have any structure that is sensible. So how could this be? Standard wisdom would suggest that the hypothesis space, the space of functions that the neural network can really realize, is huge. It contains good functions and bad ones, and in this kind of caricature, the observations from Zhang et al. Suggest that in practice we live way over to the right in this sequence of model capacity. So high in the overfitting regime, you have enough capacity to fit all the training points. And when you do that, the standard wisdom suggests that away from the training support points, the function should and does vary wildly. And that variation, should show up in the total error. When you go and measure the performance on your model in some held out test points and ask, how well do you perform on such a test set, the variation that you get kind of away from the training support points, visualized by this figure on the right, bottom right, it should translate into huge variance in your predictive function, and therefore kind of induce this upward trend in the total error as you increase the model capacity. So as you move left to right, the story goes, you should transition through a regime where you, on the left, first don't have enough capacity. In the middle, you kind of get a sweet spot, and then on the right, you're overfitting. And so you trace out this kind of U-shaped error curve. And typically that's roughly the level of rigor at which the argument is made in the standard introductory machine learning course. And in fact, the argument isn't really very rigorous to begin with, so it's probably not surprising that in practice you don't exactly see this. But nevertheless, in the last 3 or 4 years, a number of observations of deviations from that U-shaped curve expectation have circulated in the literature. And typically what is observed is something like this, where on the x-axis here is the number of parameters in the model for a different set of models. And the y-axis is a measure of the error. And you can see that over on the left, when you have relatively few parameters, you actually often do see this sort of standard U-shaped curve. But then you pass through a transitionary point, which is roughly the place where you have enough capacity in the model to memorize all the training points. And as you move to a regime where you have more parameters than that, then the error tends to descend again, carving out this kind of double descent type curve, which is the name that this phenomenon goes by typically. And often the best performing models live out kind of way to the right. So this double descent phenomenon is and has been a kind of mystery in the field? Like, how could this be consistent with the intuition I painted a second ago? Why doesn't the variance explode when you move off to the right? And then, refining this slightly further, you could say, you could make some additional observations. So here I'm showing a sequence of models in a scatter plot here, where the performance on kind of the original data distribution is on the x-axis, and then on some new data distribution on the y-axis. And you could think of this, I think a good intuition is, and many of the examples are from image classification tasks. So you could imagine the original test set are just other natural images, and you're plotting the accuracy of the model on those new unseen images. And then on the y-axis is some perturbed distribution. Maybe it's those original images, but at a different time of day, or through some kind of blur, or like with occlusions, or some kind of white noise laid on top, or some kind of shift to the distribution. So you have a new test distribution. And this type of distribution shift is, of course, important if we would like to deploy models that are robust in the real world. So that's the motivation for these things. But what is found is, as you improve the performance of the model on the original data set by, for example, adding more parameters, you will move left to right. And you find that you also move bottom to top. So there's a strong positive correlation between your accuracy on the original data set on shifted data sets. But of course, what's most striking here is that the relationship is linear, or appears to be approximately linear. So these are two categories of mysteries, so to speak, that have been prevalent in the deep learning literature in the last several years. There are, of course, way more, but I just wanted to give two concrete examples, and two examples that I think are amenable to study. And I'd just like to ask the question about, is this actually interesting? And the argument I'm going to try to make, not to give away the punchline, is no. It's just that we don't understand the backgrounds. And I guess the goal of this talk and of this line of work, broadly speaking, is to build a better understanding of the backgrounds, so we can actually do some kind of science. So that's the motivation, and that's some background from deep learning. And I'd like to describe a sequence of a couple models for which you can do explicit calculations, and introduce the methods for doing those calculations, and hopefully that will tie into some of the interests and expertise in the audience here. So bear with me through the long introduction. Hopefully it will strike a chord with you soon. So in general, for many years, the types of analyses that theorists studying learning theory tended to do would be ones that would utilize some kind of simplification that would arise in a particular asymptotic regime, which of course is expected and normal. And the two of the regimes that have been interest lately are the large data regime. Actually, this is sort of the standard paradigm for learning theory. There's a long history of results and many things you can say about generalization error and whatnot if you assume that the number of samples that you train on is much larger than any other number in the problem. Within the last few years, an alternative paradigm has emerged that's quite useful, which is kind of the opposite. It's saying, well, actually, if your model has a lot of parameters, in particular, the width, the size of the intermediate layers in your neural net is very large, then things simplify as well. And you can classify the space of functions defined by the initial random parameters in terms of certain Gaussian processes, etc. But somewhat surprisingly, actually very little has been done studying what happens when more than one number is large. And so it's surprising for two reasons, I guess. But probably the most important reason is that, in practice, if you want to talk about state-of-the-art models, more than one number is large. So Courtney, I think on Monday showed this slide, but it just shows the training data set size on the y-axis and the number of parameters on the x-axis for a set of models over the last 60 years or something that were state-of-the-art at the time. So this is a hand-curated set of points, roughly selected by some kind of interestingness metric. Maybe they opened up some kind of new domain that wasn't accessible previously or something. So, there's a lot of bias from the selection process, but still what you can observe is that there's a strong, again, positive correlation here, and the best fit is linear. So, if you want to talk about state-of-the-art model performance at a given time, it's probably the case that the number of parameters and the number of samples are both large, and as you have more computational resources, they're likely to grow large at the same rate. Another perspective on exactly the same point, which I think is interesting, is if you kind of fix a time slice, in this case, 2022, a recent paper from DeepMind looking at large language models, so natural text generation. They did an analysis to look at how to optimally tune the utilization of compute, like their computational resources. Should you add more training samples and train the same size model, or should you keep the training set size the same and add more parameters, train a bigger model? And like, what's the optimal trade-off in terms of a fixed compute budget? And when you sort of carve out this Pareto frontier, what they found is that basically there's a linear relationship. So the number of parameters and the number of training samples should scale in proportion to one another. And in fact, the raw numbers on the axes here, it's like both of them are huge. Okay, so hopefully I have convinced you that if you want to talk about state-of-the-art machine learning, you need to talk about high-dimensional asymptotics in the standard sense, or at least some notion of the standard sense of high dimensionality. And in fact, if the specific model you're interested in were linear regression, then the previous argument, suggests that you're basically talking about the standard high dimensional regime. That's because the number of parameters in a linear regression model is just set to be equal to the dimensionality of each sample. It's just a structural constraint. So if you would like the number of parameters to scale like the number of samples, that implies that your data matrix is growing large and the row and column dimension size growing at the same rate with some ratio, potentially constant factor phi. So this is all a convoluted way to argue that we need to talk about inference in the standard high dimensional sense. Except not quite, because linear regression is too simple. And that probably comes as no surprise, but because of this structural constraint that the number of parameters is essentially must be equal to the dimensionality of each sample, there's no real way to naturally manipulate a linear regression model in a manner that would induce this kind of over-parameterization that would allow us to look at these double descent type curves. Can't really change the number of parameters in the model without simultaneously changing the data distribution. So this is a problem, I think, if we would like to have a realistic explanation or intuitive explanation for this phenomenon. So while that's true, there's a very, very simple generalization to some extent, extension of linear regression called random feature regression. Now, I think Courtney and Elliot maybe on Monday talked a little bit about this, but it's very simple. If you haven't come across it, it's just linear regression, except instead of using the original data matrix X, what you do is you pass that data matrix through a layer of a neural network. So in particular, what you do is you multiply X by some random matrix here, W1, and to the result, you apply some nonlinear function little f to each entry. So this gives you some matrix capital F. And if you just regard capital F as your data set, then you can perform linear regression with that. And then that's all that random feature regression is. So what does it buy you? Well, it lets you model nonlinear functions of the data, for one. So it's nonlinear in X, but it's still a linear model in the trainable parameters. So it maintains that simplicity. And for our purposes here, what I think is very nice is that there's a strong connection to a neural network. And in fact, if you just view this model as a single hidden layer neural network, this random feature model is equivalent to training the weights of the top layer, leaving W1, the lower layer, fixed. So there's like a direct connection here to neural networks, both sort of structurally in the form and then more precisely in this kind of very simplified setting where you train the top weights. So it has this connection to neural nets, and furthermore, it has this knob that we want, which would allow you to adjust the capacity of the model independently of the data distribution. So you can change the dimensionality of this random weight matrix W1. You can change N1 at will independently of the data distribution. And that's going to change the size of your so-called hidden layer. It's going to change the dimensionality of your random feature matrix. Each random feature embedding of each sample. So the samples of this new random feature matrix F will have dimension N1, which you can adjust. And by increasing N1, you can get your model more over-parameterized if you wanted to. And then finally, this model is nice because you can solve it in the sense that you can analytically compute the test error in at least for certain data distributions in the high dimensional asymptotics I alluded to. So I'd like to talk a little bit more about this model and how we solve it. First, I just come back to the high dimensional asymptotics briefly. And because now there are in fact 3 pertinent dimensionality parameters, to be a little careful about what you mean by the high dimensional asymptotics. So what I'm going to do, and this is a choice, and there could be different interesting regimes to study, but I'm just going to assume that the data set size, the original input dimensionality N0, and this random feature dimensionality N1 are all going to go to infinity at the same rate. Okay, so this is the setting. Hopefully it should look like at least somewhat familiar. What I would like to do is compute the test error of this random feature model under some simplifying assumptions of the data distribution in these high dimensional asymptotics. So the mechanics of this is actually pretty straightforward. So here I've written the objective function L for the problem as a function of the trainable learnable parameters W. So it's a quadratic function of W. W1 here are the random feature embedding weights, this random matrix, which we regard as being sort of fixed for each instantiation of the problem. And then therefore F is fixed. The only trainable parameters are W. L is quadratic in W. There's a solution, W star, which is given in the standard way through this resolvent matrix Q. The resolvent is of this kernel matrix K, which is F transpose F. And the regularization parameter in the loss gamma plays the role of the spectral argument. And so you can write down the predictive function defined by the optimal solution to this objective function W star. And that function is computed in a simple way. You first take your unseen test point, x tilde, your new point. You pass it through your random feature embedding to get this f tilde. And then you apply W star. So to compute the test error, you just take the expectation of the squared error of your prediction minus this target, which in this case, y tilde, I'm assuming it's just a linear function for some coefficient vector beta. And I'm assuming some simple distributional assumptions on the data. In particular, it's just standard Gaussian, uncorrelated standard Gaussian. And so I mean, like what you do, you just turn the crank and try to calculate this expectation. And what you find, you get a sum of some tracial objects that involve the resolvent or powers of it, the label matrix Y and the random feature matrix F. And so how do you actually simplify that? How do you compute these things? At first glance, it looks very challenging because of this nonlinear function, little f, that defines this random feature matrix. So what you do, hopefully this doesn't come as a surprise. What you can do is just basically just replace the random feature matrix that's nonlinear with a linearized surrogate. So you choose some matrix F-lin and you design it so that it maintains the low order correlation structure of F. And computing up to the second moment, you can confirm that if you choose the constants in the right way, that this linearized matrix has the same low order correlation structure as F. Here A is just some auxiliary random Gaussian matrix. And then you can, just use sort of standard arguments, concentration of quadratic forms, basically, to show that the Cauchy transform of the random feature kernel is the same if you replace F with the linearized version, and through some additional arguments, rewrite the test error in terms of that Cauchy transform, and essentially that's all there is to it. You can also try to do a replacement strategy, which is a little bit more complicated. We're still working on writing that up, but it could be useful in a slightly more general case to try that. But so basically you just do this replacement, and then you can turn the crank. And when you get rid of all the nonlinearities by these substitutions and simplify the resulting tracial terms, when the dust settles, you end up with something which is kind of linear or quadratic in the resolvent. And essentially what you want to do is evaluate the trace of a rational function of random matrices and evaluate this asymptotically in the matrix sizes. And of course, this is a solved problem for this type of trace object. You can just write down a linear pencil and then turn the crank using the formalism of operator valued free probability to compute self-consistent equations for the relevant trace objects. And when you do that, you get pretty much what I think you would expect, a set of coupled polynomial equations in terms of which you can express the test error. So I won't go through the details, but when you numerically evaluate those results, this is what you get. So probably simplest just to look at the right panel and the solid curves in blue, for example, which correspond to small regularization. The x-axis you could think of as the number of parameters, the y-axis is the error, and you can see that you are exhibiting this double descent shape. And so, I mean, there's obviously a lot one can say. You have the explicit form of the equations and whatnot. So there's a lot of detailed analysis you could do. But the point I would make, just for a high level conclusion at least, is that this double descent behavior, which I mentioned was sort of this ongoing mystery, it occurs in this simple setting, right? The data in this case was uncorrelated Gaussian. You have this random feature model, which is very boring. Yes, there's a nonlinearity, but it doesn't really resemble modern practice for neural nets too strongly. The data is, again, isotropic. The target function was linear. Like there's nothing that resembles natural data or the real details of deep learning, and yet you still see this behavior. So, one perspective on this, I wouldn't want to push it too hard, but basically this is background. I mean, this is what you would expect to see. There is nothing interesting happening, and you still get this behavior. So here's a null model of double descent, which you could solve and leverage tools from random matrix theory to actually draw these kinds of insights. So I'll just quickly talk about this other mystery. I won't spend a long time, so I know we're running a long time, but you can kind of generalize this analysis in a natural way to talk about the differences between in distribution generalization error and out of distribution generalization error when you have a test set that has a somewhat different distribution than the training set. The idea here, and there's sort of many ways you could think about approaching it, but a simple one is when the covariates are distributed somewhat differently. And I think the easiest way to do that is if you assume that the training points have some covariance sigma train and the test points have a potentially different covariance sigma test. And basically you can pull the crank through the same kind of calculations and get similar kinds of formulas. I would just maybe give one example for the kind of distribution shift that you might think about, and some intuition for what it would look like. So in the very simple case where the covariance is diagonal, if you just look at the bottom of this slide for an example for small n, if you have maybe one large eigenvalue and a bunch of small eigenvalues for your training covariance, and your test covariance is the same but raised to the theta power and normalized, then you could ask, well, what do you expect to happen as you vary theta? And the intuition should be, well, when theta is very large, when it's bigger than 1, the test set is going to emphasize the large eigendirections more. And since the algorithm is learning to emphasize the large eigendirections as the training set, because they're the dominant ones there, when you test on those eigendirections preferentially, you will have better performance. And conversely, if theta is less than 1, you're going to emphasize these weak eigendirections, performance will be worse. So the intuition should be you should see a performance boost as you increase theta. So theta is just a parameter here that's kind of like varying the strength of the distribution shift. Okay, so this is far too much information at the moment, but just look at panel E on the top blue line. You can see what I said, right? So this is our theoretical prediction. And indeed, you find that as you increase theta, the error goes down. So, but the main point I want to make is that you can pull the crank a little further and actually just prove that the test error on the unshifted data set is a linear function of the test error on the shifted data set. So if you follow this specific form of covariate shift and you do things parametrically in the model size, and you carve out these exact linear trajectories in this plane. And so I kind of fine-tuned the theta parameter here so that it resembles the figure on the right, which is from real data. But you can see that you can reproduce this phenomenon exactly, capture the main qualitative behavior and everything in this basically completely trivial setting. So for a similar reason, I might argue, although perhaps with slightly less evidence, but still I think it's basically the case that these linear trends are not really interesting in the sense that they follow from trivial model in high dimensions. So you might think of it as background. So I'm basically out of time. I would just emphasize that, I tried to give some evidence that the deep learning models are operating in the high dimensional regime, that in fact, the community at large has a lot of unexplained phenomena, and nobody knows what's going on. That you can explain some of these things are pretty simplified models that are actually tractable, and there are a lot of open problems that I hope some of you might be interested in working on. So thank you. Let me stop there. Thanks for your attention.